Okay, I built, this circuit here, and here's a circuit board to it. And what it is basically a, um, circuit got out of this, Hazen book, and that I built up a while back, and I already knew it worked because I tested it before, but unlike a lot of the circuits I'm showing you, not really tested them before the day I show you. But that's the actual board built up, and it's meant to be, kind of like a 741 OpAmp, crudely speaking. Um, and I've got it rigged up, as a non-inverting amplifier, and I'm able to do this with a single resistor because, as you see over here, if you look at my mouse cursor, there's a 1K resistor I got built in, that's automatically going to one of the inputs. So I got like a 27K resistor there, and theoretically it should be a gain of 27, but this ain't no perfect op amp. However, you know, here's the result of me putting, that signal into it. About 320 millivolts, and you can see the peak-to-peak value up here. Output is like 21 volts. As I'm powering it by, plus or minus 12 volts. Um, and peak to peak input is that, and the gain is about, well, it's about 29 actually. So yeah, that's because it should be about 28, with that. So it's actually working out fine. Earlier it seemed a little low, but maybe that's because I was putting a lower signal in. I was trying to test its maximum range, and it's like I said, if I move that up, it'll start to clip. Oops, shit, I didn't mean to change the frequency. But if I move that up, it'll start to clip at some point, and maxes out at 22 volts. So, you can see the clipping happening. But, if I pull it down to, where, like I said, it's, for such a large output swing, it's got really good distortion. I mean, I'm at, 1 kilohertz. Let's try a square wave and see what that looks like. It looks really fucked up on the inputs, because that's the other thing. This is direct driven too, just like the differential amplifier. There's no input capacitors on it, so this is direct drive. So, um, you know, but yeah, I mean, its output square wave looks good. Its input square wave looks a little dodgy here for, like it's got some capacitance on it. Let's see. I don't know if that's because of that compensating capacitor I have in it here, but I'm not really sure. But yeah, I'm actually surprised it looks that good on the output. But let's see. Try that noise signal there. Pulse. Trapezoid. Like I said, the input doesn't look anything like it, and it's pretty substantial at 367 millivolts. But boy, the output's a perfect copy of what it's supposed to look like. So that's really curious. Kind of wonder what's up with that. But anyway, the gain's still 27. Again, it's supposed to be 28 because it's a non-inverting amplifier I got it set up as. So, power sign. But yeah, I'm surprised it looks that good. And this should couple right down to DC too, because it's not got any input caps on it. So, let's see, where are we at? Microhertz, okay. So, man, at 1 hertz, we're getting good square wave. So, you know, yeah, it's pretty impressive. Just our input signal looks better now. Up the frequency over here at 2 hertz. Seven hertz. So about 8 kilohertz, everything goes to shit, which doesn't surprise me, because this thing only, you know, is, like I said, not perfect. It's only going to have so much gain to it. Now, let me see. Because part of this could have been, okay, well, maybe it was the, no, it was the analog discovery doing that. Remember, I was, in a previous video, I was telling you about how analog discovery's got some kind of built-in filter that will basically drown out higher frequencies based on what, you know, and I don't know if you can turn that off or not. Again, it's one of the reasons this thing doesn't alias, but it also means if there's a signal there, you're not really seeing what's really going on, because it kind of scales everything in an appropriate way, but it can hide high enough frequencies completely. So that's what you just kind of saw there. But yeah, no, our output still, you know, 21 volts even at, you know, 8 kilohertz. So, you know, seeing some distortion. Again, part of that makes me wonder if it's the input signal, because that's really strange, you know, what it's basically doing. Take the frequency up a little bit more. Okay, you're starting to see some ringing in it, but overall, it's not too bad at 38 kilohertz. Okay, now we're starting to see some effects. So now we're starting to hit its distortion limit, or whatever you want to call it. So, you know, right around 75 kilohertz, actually. It's for a gain of, you know, Jesus, the gain's apparently gone up to 42. That's interesting. Wouldn't expect the gain to increase by that much. Yeah, it's still at 40, even as I reduce the frequency down to 5 kilohertz. So let me change time step. So yeah, it's saying the gain is you know, 37 now. That's not that's unexpected. I kind of wonder if there's something wrong with the calculations here, honestly. Now see, now we're back down to 27. But, okay, our peak to peak signal is, you know, at 700 millivolts, which is where it's supposed to be, but, you know, but it's falling precipitously while the output is, so we're probably clipping it a little bit. I probably ought to reduce the amplitude maybe a bit, just to make sure. But, no, the gain's still 40. Shit, you can't see any of this, can you? Sorry about that. But yeah, it's, you know, very interesting how this thing works. I think I'll do a network sweep on it. Guess I'll just keep it to this default range. Single. Alright, back. Yeah, so you see a hump, you know, there is a you know, yeah, I guess about there is appropriate. See, right about here at about, you know, 450 kilohertz, there's a big increase in gain, you know, but generally it's around 25 to 27 or so. But yeah, that's interesting, you know, unless you get that kind of hump. I have something to do with a compensating capacitor or something, I don't know. But yeah, it's got surprisingly good performance for, you know, something you cobble together with, you know, half a dozen transistors. You know, it's usable, you know, usable gain out there. And one of the nice things about this is, you know, is the voltage. You know, I get plus or minus 12 volts, but since you're using discrete transistors, you could actually make this a higher voltage op amp. you know, if you did your due diligence with it, of course. But you know, instead of being stuck with a typical plus or minus 15 volts, you know, what the most op amps have, you know, you could actually make it a higher voltage op amp because it's discrete. Again, it depends on what you're going to do with it, and you know, um, everything. But yeah, it's a pretty neat little circuit. Like I said, it's pretty easy to build, and um, you know, that's the circuit board. If I hadn't showed you that already. So anyway, that'll take care of this. Cheers. Oh, oops. It's still running. I was using Corel capture here so I can capture the screen too.